Okay, so here's part 2. We're going to do or begin section 8.3, power series solutions to linear differential equations. So we're just going to look at a second order linear differential equation in standard form. So in standard form, it looks like this, homogeneous. That's what we're looking at in this section. And if you have a homogeneous linear second order differential equation in standard form, and it's part of an initial value problem, then you want to look at your x0 in this initial value problem. And we say that x0 is an ordinary point of the differential equation if the functions p and q are analytic at that point. Remember what that means. To be analytic at x0 means that p and q have power series representations centered at x0. If that's not true, if one or both of them, of those functions, if either p and or q are not analytic at x0, then x0 is a singular point. So let's look at an example of just trying to identify what kind of point x0 is. So let's look at this differential equation. X y double prime plus x times 1 minus x to the negative 1 times y prime plus the sine of x times y is equal to 0. Okay, first thing we want to do, of course, is put it into standard form. So divide everything by x. So my p then is here. That's 1 over 1 minus x, that's my p. And sine of x over x, that's my q. Okay. All right, we want to know where are p and q analytic. Well, p, it's just a rational function, so p is analytic everywhere in its domain. Well, the only place it's not defined is at 1, so it's analytic everywhere except x equals 1. And how about q? Q is actually analytic everywhere. And a little weird thing going on there. Maybe we saw that before actually in an example. It looks like it's not analytic at 0. In fact, it looks like it's undefined at 0. But when we're talking about analytic, we're talking about a power series representation. So if we want to ask about is it analytic at 0, I have to see if I can come up with a power series representation centered at 0. Well, I can write the sine of x over x as 1 over x times, and then take the power series representation centered at 0 of the sine of x. So that's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And that would simplify to just 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial, and so on. And there I have a power series representation of sine x over x centered at 0. So because I have one, it means it's analytic at 0. Well, I guess I should say at x0 equals 0, and this one up here should be except x0 equals 1. Okay, so what are the ordinary points? Ordinary point is a point x0 where both of them are analytic. The only problem either of them has is at x0 equals 1. So that's the only point that is not ordinary. In other words, x0 equals 1 is a singular point, and all others are ordinary points. Okay, now the reason why we care about ordinary versus singular is this fact. If x0 is an ordinary point, then we can find solutions that are power series, power series centered at x0. Such a solution will exist. If x0 is an ordinary point, then there is a power series solution to the differential equation centered at x0. Okay, so here's an example where we find such a solution. So let's use power series to solve this one. 2y double prime plus xy prime plus y is equal to 0, and our instructions are find a power series solution about the point x0 equals 0. All right, well, if our instructions are to find a power series about x0 equals 0, maybe we might assume that 0 is an ordinary point. Otherwise, why would they ask us to do that? But I think it's always a good idea to check. Books can make mistakes. Teachers can make mistakes. It could be that this problem is not answerable. If 0 were a singular point, then we can't proceed with what we have learned so far. So let's check for the first, before we find the solution, check that 0 is in fact an ordinary point. So I write this differential equation in standard form, dividing everything by 2. Okay, I identify my P and my Q. Okay. And I see that they are both analytic at 0. In fact, they're both analytic everywhere. All I care about, though, in this problem is that they're analytic at 0. So this x0 equals 0, this is, in fact, an ordinary point. And so I know I will be able to find a power series solution. Okay. So my solution, y, I know I can write it as a power series centered at 0. So if I do that, it's going to look like this. And in order to figure out what this solution looks like, I need to find those coefficients. Okay. So in order to find the coefficients, what I'm going to do is I'm going to differentiate y twice and then plug it into the differential equation and see what I get. Okay, so y prime, differentiated. The first term of the series is a constant, so when I differentiate, that is going to vanish. So I start only at 1, and then I have an times nx to the n minus 1. And then I'm going to differentiate again. In y prime, the first term is a constant. That's going to drop away when I differentiate. So my new series starts at 2, and then I have an times n minus 1 times x to the n minus 2. Okay. And now I want to substitute these into the differential equation. Okay. So my differential equation looks like 0 equals y double prime plus x over 2 y prime plus 1/2 y. Okay, so I want to substitute all those series in. So y prime, what's this? I've got the sum as n goes from 2 to infinity of an. Actually, it's more traditional to put the n's first. So let me put n times n minus 1 times an times x to the n minus 2. There's y double prime. Okay, plus x over 2 times y prime. Y prime starts at 1, and I've got, there it is, n an x to the n minus 1 plus 1/2 times y. Y is the sum as n goes from 0 to infinity of an times x to the n. So this whole expression here, the sum of 3 series, is equal to 0. My goal here is to figure out what the ANs are. Now, if you have, and we talked about this in the last section, if you have a series, one power series, and it is equal to 0 for all x, then all the coefficients have to be 0. That's the fact that we want to use. We basically want to equate coefficients, right? On the left-hand side, I've got 0, which you can think of as a series with all the coefficients being 0. The right-hand side, however, right now is 3 different series added together. So I want to combine them all so that the right-hand side is one series. And if I can do that, then in that one series, all of the coefficients will have to be 0. Okay, so this is my next step, is to figure out how to combine these. So first of all, in order to combine them, I need to have all the powers of x be the same. You know, when you collect like terms, you collect like powers of x. So I want all those powers of x to look the same. Rather than n minus 1, and n minus 2, I want them all to look like n. So I'm going to accomplish that with a shift of index. But now before I can do that shift of index, there's one issue I have to deal with, and that's the fact that there's this x right here sitting outside. That's not any good. That needs to be inside and part of the series. So the first thing I want to do before I start shifting indices is to bring that x into the middle series. So, you know, I know you couldn't do this if you were handwriting it, but I can do it here, so why not? Copy, paste. All right. Get rid of that. All right, so what I want to do is I want to bring this x in. So if I bring the x in, just leaves a 1 out here, and what happens is this power x to the n minus 1 just becomes an x to the n. Okay? So that's my first step. Okay, now I want to combine them. To combine them, I need like powers of x. I got x to the n in 2 of the series, that's great. But the first series has n minus 2, so I want to do a shift of index on that one. Okay, so I'm going to do my copy and paste thing again. All right, so that's there. And in fact, I want to just, I'm not going to go too cheater on this. Let's erase this. I'm going to rewrite that part. Okay, so I want to shift indices in that first series. So I want it to have a power of just n. The original series starts at 2, and then the exponent is n minus 2, so the exponent is 0. So this one will start at n equals 0. And everywhere I see an n in there, I need to replace it by n plus 2. So I'll get n plus 2, n plus 2 minus 1, so n plus 1, a sub n plus 2, and x to the n. Okay, now I'm ready to combine my series. But there's one other thing that is in the way of me combining the series, and that's the fact that they don't all start in the same place. So I would have to have them all starting at n equals 0 or all starting at n equals 1 if I were to be able to combine them. So what I'm going to do is pull off the 0 term in the first series and just put it off separately, and then also pull off the 0 term in the third series and just pull that off separately. And then what I'm left with is 3 series. They all start at n equals 1. They all have a common x to the n, and I can combine those. Okay? So first of all, I'll take the n equals 0 term from the first series. So that's 2 times 1 times a2 times x to the 0. Okay. Then I'm going to take the 0 term from the third series. So that's going to be 1/2 a0. Okay. And now after pulling out all those, what I'm left with is, and we can make an extra step. Normally I wouldn't want to rewrite all this, but since I'm able to do this copy-paste trick, it works out pretty well. So what I'm left with when I do that is this. I get that stuff plus, and then these two are now starting at 1. So if I scroll down, maybe you can see what I've done. I've taken the 0 term from the first series here and pulled it off and put it right there. And I've taken the 0 term from the third series and I've pulled it off and I've put it there. And after having done that now, all 3 series here all start at 1. So they all start at 1, they all have x to the n, and those can now be combined. All right, so combining them, I have 2a2 plus 1/2 a0 plus the sum, as n goes from 1 to infinity, of n plus 2 times n plus 1 times a sub n plus 2. And I'm going to factor out that x to the n because it's common in all of them. Plus 1/2 n a sub n plus 1/2 a sub n times x to the n. Okay, and that's, we're all done with our right-hand side. We've combined it into a single series, and notice it's a power series. That first thing in parentheses, this guy right here, that's my constant term. That's the coefficient of x to the 0, and then the rest of it is put together in this series from 1 to infinity. So what you're looking at right there is a single power series, and it's equal to 0. So that means all of its coefficients are equal to 0. So I'm able to conclude that this thing has to be 0, and this thing inside parentheses, that coefficient, that is 0 for every n. And we can use those two facts to figure out what our a_n's are. Okay. This video is now a little long, so let me stop this. We'll make a part 3 in which we use these new equations that we've just got to figure out what the a_n's are. So make sure you review this and make sure that you know how I got where I got and that you understand this whole part first. This is a key part, and this is a natural break in the process of solving it. So review this video if you need to before going on to the next one. And in the next one, we will solve for a_n.